Hello! Today, we're going to dive into a famous and historically fascinating problem in number theory. By the end of this video, you will be able to prove that there are no solutions to a simplified version of the problem and understand the core challenge of the original. The problem we'll be exploring is known as the Brocard-Ramanujan equation. This equation asks a seemingly simple question. Are there any positive integer solutions, or pairs of integers n and m, that satisfy the relation n factorial plus 1 equals m squared? In other words, when does a factorial plus 1 result in a perfect square? The equation is n factorial plus 1 equals m squared, where n and m are positive integers. This problem was first posed by Henry Brocard in the late 19th century, and later by Srinivasa Ramanujan. It looks straightforward, but it's deceptively difficult. In fact, it's still an unsolved problem. Before we start, let's refresh our memory on what factorials are. A factorial, denoted by an exclamation mark, is the product of all positive integers less than or equal to a given integer. So, n factorial is 1 times 2 times 3, all the way up to n. Let's list the first few factorials to get a feel for how they grow. 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 6 times 4, giving us 24. And 5 factorial is 120. So we have 1, 2, 6, 24, 120, and so on. Now, let's plug these values into our equation. N factorial plus 1 equals m squared, and see if we can find any solutions. When n is 1, we get 1 factorial plus 1, which is 1 plus 1, or 2. Is 2 a perfect square? No. For n equals 2, we have 2 factorial plus 1, which is 2 plus 1, or 3. Still not a perfect square. What about n equals 3? 3 factorial plus 1 is 6 plus 1, which is 7. No luck. Let's try n equals 4. 4 factorial plus 1 is 24 plus 1, which equals 25. Is 25 a perfect square? Yes, it's 5 squared. So, we found our first solution pair, n equals 4, m equals 5. The pair, 4, 5, is a solution. What about n equals 5? 5 factorial plus 1 is 120 plus 1, which is 121. Is that a perfect square? Yes. 121 is 11 squared. So, we have a second solution pair. N equals 5, m equals 11. The pair, 5, 11, is another solution. Let's check one more for n equals 6. 6 factorial is 720. So 6 factorial plus 1 is 721. A calculator shows that 721 is not a perfect square. 26 squared is 676, and 27 squared is 729. So it's close, but no. So far we found two solutions, 4, 5, and 511. There's one more known solution, 771. But are there any more? Nobody knows for sure. The only known solutions are 4, 5, 511, and 771. Computers have checked this equation for values of n up to a staggering 10 to the power of 9. That's 1 billion, and they haven't found any new solutions. This suggests that there likely are no other solutions, but proving that is the real challenge. The tools needed to tackle the full Brocard-Ramanujan equation are quite advanced. However, we can use a simpler version to demonstrate the same style of reasoning. So, let's shift our focus to a related problem. By the end of this next section, you will be able to prove that the equation n factorial plus 2 equals m squared has no solutions for n greater than 2. In this scene, our goal is to prove that a similar equation, n factorial plus 2 equals m squared, has no solutions when n is greater than 2. Let's make that our objective. We will prove that n factorial plus 2 equals m squared has no integer solutions for n greater than 2. How can we prove something like this? A very powerful method in number theory is modular arithmetic. By looking at the remainders when we divide by certain numbers, we can often reveal contradictions. The general idea is to pick a number, called a modulus, and examine both sides of the equation. If the equation holds true, then the left side and the right side must have the same remainder when divided by our chosen modulus. If we can show they have different remainders, we prove no solution exists. So, our strategy is to use modular arithmetic. Our plan is to take the equation n factorial plus 2 equals m squared, choose a modulus, and check if the remainders are consistent. Let's test this equation for small values of n. This helps us build intuition. For n equals 1, we get 1 factorial plus 2, which is 1 plus 2, or 3. Not a perfect square. For n equals 2, we have 2 factorial plus 2, which is 2 plus 2, or 4. This is a perfect square, 2 squared. So 2 is a solution. So we have a solution at n equals 2. But we want to prove there are none for n times greater than 2. This is a crucial distinction. Now, let's pick a modulus. We want a modulus that simplifies the n factorial term. What's a good choice? Any prime number less than or equal to n. This will make n factorial equivalent to 0, modulo that prime. For n greater than 2, the number 3 will always be one of the factors in n factorial. Therefore, for any n greater than 2, 3 divides n factorial. What does this mean in terms of modular arithmetic? It means that n factorial is congruent to 0, modulo 3. In other words, the remainder when n factorial is divided by 3 is 0. This is true for all n greater than or equal to 3. For n equals sign 3 equals 6, and 6 mod 3 is 0. For n equals sign 4 equals 24, and 24 mod 3 is also 0. Now, let's look at our equation. N factorial plus 2 equals m squared, and reduce it modulo 3. We can rewrite our equation in modular form. N factorial plus 2 is congruent to m squared modulo 3. For n greater than 2, we know that n factorial is 0 modulo 3, so we can substitute 0 into the left side. This simplifies our congruence to 0 plus 2 is congruent to m squared modulo 3, or simply 2 is congruent to m squared modulo 3. So, if a solution exists for n greater than 2, m squared must have a remainder of 2 when divided by 3. Is this possible? Let's check all possible values for m modulo 3. Any integer m can be represented by its remainder when divided by 3, which is either 0, 1, or 2. Let's see what m squared becomes in each of these cases. If m is 0 modulo 3, then m squared is 0 modulo 3. If m is 1 modulo 3, then m squared is 1 modulo 3. If m is 2 modulo 3, then m squared is 4, which is 1 modulo 3. Take a moment to think about what we just found. We checked all the possibilities. We saw that any integer m squared, when divided by 3, must leave a remainder of either 0 or 1. It can never leave a remainder of 2. In summary, the only possible remainders for a perfect square modulo 3 are 0 and 1. 2 is never a remainder. This creates a contradiction. On one hand, for the equation to hold we need m squared to be congruent to 2 modulo 3. On the other hand, we just proved that m squared can only be 0 or 1 modulo 3. Since a number can't have 2 different remainders when divided by 3, we've reached a logical impasse. This means our initial assumption, that a solution exists, must be false. Our argument by contradiction is complete. The left side must be 2 modulo 3, but the right side can only be 0 or 1 modulo 3. This is a contradiction. Therefore, we can conclude that there are no integer solutions to the equation n factorial plus 2 equals m squared for any value of n greater than 2. We have successfully achieved our learning objective for this scene. Now, let's return to our main problem, the Brocard-Ramanujan equation. Our learning objective for this final scene is to understand why our modular arithmetic trick doesn't work for n factorial plus 1 equals m squared. Our goal is to understand the obstacle that modular arithmetic faces with the original Brocard-Ramanujan equation. Let's try to repeat our process. We had our equation, n factorial plus 1 equals m squared. We need to pick a modulus. Just like before, we'd like to pick a prime that's less than or equal to n, to make the n factorial term disappear. We proved that n factorial is 0 modulo 3 for n greater than 2. Let's try using the modulus 3 again. For n greater than 2, we reduce our equation modulo 3. We get n factorial plus 1 is congruent to m squared, modulo 3. Again, since n is greater than 2, n factorial is 0 modulo 3. Substituting 0 gives us 0 plus 1 is congruent to m squared modulo 3. This simplifies to 1 is congruent to m squared modulo 3. Now we have a statement. M squared must be congruent to 1 modulo 3. let's check our table of squares modulo 3. If m is 1 mod 3, m squared is 1. If m is 2 mod 3, m squared is 1. So it is possible for m squared to be congruent to 1 mod 3. Take a moment to see the difference. With n factorial plus 2, we needed m squared to be congruent to 2 modulo 3, which was impossible. Here, we need m squared to be congruent to 1 modulo 3, which is possible. The modulus 3 doesn't help us find a contradiction. All it tells us is that if a solution exists for n greater than 2, m cannot be a multiple of 3. You might be thinking, what if we choose a different prime? Let's try 5, which is a prime factor of n factorial for n greater than or equal to 5. What happens when we look at the equation modulo 5? For n greater than or equal to 5, n factorial plus 1 is congruent to m squared modulo 5. Since 5 is a factor in n factorial is 0 modulo 5. So, our congruence becomes 1 is congruent to m squared modulo 5. We need to check if 1 is a possible remainder for a square modulo 5. Let's see. If m is 1 mod 5, m squared is 1. If m is 2 mod 5, m squared is 4. If m is 3 mod 5, m squared is 9, which is 4 mod 5. If m is 4 mod 5, m squared is 16, which is 1 mod 5. Notice again that 1 is a possible remainder for a perfect square modulo 5, so the modulus 5 doesn't give us a contradiction either. It tells us that m cannot be a multiple of 5. The heart of the problem is this. N factorial plus 1 is always just 1 more than a factorial. When you take a number modulo a prime that divides the factorial term vanishes and you're left with 1 modulo that prime. And it turns out that 1 is a perfect square modulo every prime number. This means that no matter what prime p you choose, if p divides n factorial, the equation modulo p will reduce to 1 congruent to m squared modulo p, which is never a contradiction. This is why the problem is so difficult. Modular arithmetic, by itself, is not strong enough to solve it. This is why mathematicians have turned to more sophisticated tools, like elliptic curves, to search for and prove the existence or non-existence of solutions. Today, we've introduced the Brocard-Ramanujan equation, discovered its only 3 known solutions, and then took a detour to a simpler solvable version to understand the powerful technique of proof by contradiction using modular arithmetic. Finally, we saw why this specific technique fails when we return to the original problem. You now know that this innocent-looking equation is a deep mathematical mystery, a testament to the fact that the simplest questions can often be the most profound. Thank you for watching.